So today we're going to talk about support vector machines. Just to show of hands, who's actually used support vector machines? I'm sure, like everyone, lots of people have used it and haven't really necessarily studied how they work. Does anyone know why they're called support vector machines? Okay, so support vector machines are a really terrible / really awesome name because they it's really catchy, and everyone has heard of them, but very few people know what the heck these English words. Did I spell it right? Like these words, English words, don't really convey the right intuition about what they are. And so I know a better way to describe it is a max margin linear classifier. That's how I like to think about it. They also extend to max margin kernel machines, and that gets into stuff we'll talk about next class. But everyone calls them SVMs now, or support vector machines, and you can just think of them like the way you think about Google. Like it's just a catchy name that people, its inventors thought of, and now we just use it. It's not really, the meaning is not like, this is being recorded, right? So I don't find the meaning all that intuitive. Okay, so let's see. So properties of support vector machines. So support vector machines are discriminative. And what that means, that's sort of in contrast to probabilistic. So you guys studied logistic regression, which is a probabilistic method. Support vector machines aren't probabilistic. There is some research on how to sort of take a support vector machine and convert it into a probability distribution. There's work we're actually going to see in the slides, some relationships between support vector machines and logistic regression, but it's really, the bottom, or the base representation, the base definition of a support vector machine is not at all probabilistic. It's just a classifier. It's just a function, or it's a function, f of x that tells you, is it in the class or is it not? I guess generally it's going to be something like this. Right? It's a binary classifier. F of x tells you, oh, sorry, that's not right. Well, this is one way to view it, but usually it's actually done like this. It's f of x. Is it, if it's greater than 0, then you get +1, and if f of x is less than 0, we get -1. So it's just a function that tells you, is it in class 1 or is it in class 2? And you can sort of think of this as kind of probabilistic, because if f of x is really, really positive, then it's like you're really confident that it's +1. And if f of x is really, really negative, you're really confident that it's -1. That's not really what it means. And when you look at the loss function, the training function that we use for support vector machines, you'll see that the training objective doesn't care at all how much, how good or how confident you are in those predictions. It just cares what you get right. Okay. So let's see. The basis of support vector machines, the reason that it was invented comes from, or let's see, the way I like to justify it, I'm not sure if the original authors actually justified it this way, is it's kind of like Occam's razor. It's kind of like in science, when you see evidence, you want to explain that evidence in the simplest way possible. You don't want to use some really complicated explanation to justify what you're seeing. So the support vector machine is going to try to do that mathematically in some mathematical way. Okay. So to start off, who can tell me? Actually, I'm genuinely asking because obviously I'm not teaching this class. So what have you guys studied with respect to the bias-variance trade-off? I saw that was on the schedule. So who can tell me what the bias-variance trade-off is?
Is that the model gets more complex, you have more variance, but less bias, and the opposite.
Okay, so what are bias and variance?
Bias comes from the error of the model you're building.
Yeah.
And the variance comes from the limited data you're training on.
Right. Okay. So
it's like two kinds of error that you're doing. Right?
Yeah. Yeah. Okay, so now what if what if there's a situation, so what if there's a situation where there's no error in your training data? What does that mean with respect to bias and variance?
It's overfitting, so the bias would be high and the variance would be
No, that's, is it the other way around? I always
The
forget.
opposite.
high.
Yeah, yeah, that's okay. Yeah, I never can remember what the difference between which one is bias and which one is variance. But the point is that, right, if you have no error on training, there's a good possibility you're overfitting. Not necessarily. You might be doing well. You might actually have a good model. But what the problem is that there's nothing protecting you from overfitting. So to sort of illustrate this, let's think about 2D data. So we'll have, just a 2D plane, and let's say, you have age on the x-axis and you have height on the y-axis. And let's say we have some data, we have some, undergraduate students who, live around here. I guess they're a little bit younger, and we have graduate students who live around here. Okay, and for some reason we only got 6 data points. Maybe this is like we're just trying to make a prediction based on our research group or something. Okay, and if we think about a linear classifier, so in 2D, I guess the math is pretty straightforward. A linear classifier looks like W is the classifier, we multiply by X, and you have some, and you have a, well, this is bad. This is also called a bias. So you have an offset. Yeah, right. This is just a scalar offset, and then this is the slope of the line, and then in 2D it's the slope, and so it's what we learned in 7th grade or 8th grade. And we say this is the function. This is the f of x. That the question is it greater than 0? That's a basic linear classifier. Okay, and so there's lots of linear classifiers available to us to separate undergrads from graduate students in this data set. Okay, we can draw this one, we can draw this one, we can draw this one. And so a linear classifier is actually really powerful compared to this data set. And so SVMs, or max margin linear classifiers, try to avoid this problem. And the way they try to avoid this problem is by limiting, or by thinking of something a little bit less powerful than just a line. And it's essentially, you can think of it in 2D again as a really, really fat line. So, if your line is, see if I can do this. If your line looks like, no, it doesn't work. Right, so this is kind of fat. It's not that fat. So if your line has to be this thick, this is really your only option. If that's the thickness of your line to separate the data, you can't rotate this and still separate all the data. So the idea is we're going to try to write down the math to make this work. So you can sort of view this as, I guess the way that the math actually works out is that this looks like there's a linear classifier down the middle, and we try to maximize this margin. But you can also think of it as we're trying to make our hypothesis class this big fat separator, and then in some ways you can think of whatever's in this middle point as like we don't know the answer. If we got an example in there, the linear classifier would say, oh, that's an undergrad. But in some ways you can think of the intuition behind that SVM is that we don't actually know the answer to that. In practice, we would just say it's an undergrad, but in terms of the objective function we're going to try to maximize when we do learning, we're going to pretend that we can't handle the situation. Okay, so, all right, so now let's see if we can warm the projector again. Get to the slides that we put together. Oh, this is too bad. All right, well, I can just talk through the slides while it warms up. So, let's see. A lot of this is actually what I just covered. So, yeah, so like naive Bayes and logistic regression are also, are examples of probabilistic classifiers, and discriminative approaches, are generative classifiers, or generative learning models. So naive Bayes and it's only an example of this. So in naive Bayes, you can actually go from just the model and generate simulated data. Whereas with a discriminative approach, like logistic regression, you don't really have a model for what X is. So you remember logistic regression, you guys are learning this probability, right? You're learning this thing. It's parameterized as a linear function, but this is the high level view of logistic regression, or really any discriminative probabilistic approach. And here, we can pull this up now. So, so in this situation, it's discriminative because you don't really have a way of saying, I'm going to now try to simulate data from this, because we don't know anything about P of X. At least from the model. The model doesn't know anything about it. You could learn that, and then it would become basically a generative model instead of a discriminative one. You guys read the XKCD comic where they're trying to install something, and then in the next panel, like they're like escaping sharks, and they're trying to get it back to the back to how things were, but every time you try to fix something, it gets worse. All right, so I'm going to try to display this PowerPoint not as a slideshow, but just show you the things on the screen. Let me just get rid of that. Get rid of that. Okay. I don't know why the presenter mode is failing. So that's all right. So this is what I was just talking about. So now what we're doing is this last bullet point. We're going to learn a discriminant function, f of x, that isn't probabilistic initially. Again, there's research that's extended back to being probabilistic. But before we move on, this picture that Drew put on the slide is kind of fun. You can't really see it. But it's just like a sign that says support vector machines. And this was a few years ago. The students at Carnegie Mellon, like they had a protest, but like they weren't protesting anything. They just had like signs that had like inside machine learning jokes. Now I realized I read about this on the internet. I wonder if Drew was actually there. It's very funny. But like it's so funny. Like, the funniest part is that only like a very small handful of the world understood what was going on. Okay. So this is the same picture I drew before. So the question is, if you have to pick a line, which line is better? And the answer is this. And I wanted to say that this slide, so Drew posted the slides to this. There was a bunch of equations over here. I deleted them from this copy because I didn't know what one of them meant. So I'm gonna show you my derivation for this, and then you can ask Professor Batra later what that other line meant. So I guess I'll just write on the side of the board here. So like I said, the hyperplanes are the separator. The separating, this line right here is defined by, a simple linear algebraic expression. Okay, it's that defines a plane in high-dimensional space, right? Okay, so then now the question, our classification is, the idea is which side of the plane are we on? But if we don't want to make it a fat hyperplane, we're going to do this. We're going to have, and it's hard to see, it's really small, so we're going to have two things. We'll have one version, which is the space of things where this discriminant function is greater than 1, and then another space of things where this discriminant function is less than -1. And then in between, we're just going to say, I give up for now. And for now, and this tells us that the actual label is it's a positive label if it's greater than, the discriminant function is greater than 1, if it's a negative label if the discriminant function is less than -1. Okay, so that's fine, but the problem is that, right, we don't know what B and W are, and so what this thing actually means is very little in terms of how thick. Stop this one. Okay. This doesn't actually tell us anything about the margin, about how fat that thing is, because you could just always rescale this W and sort of change how thick that thing, this vector, you can think of this vector as the margin. So let's try to write down a mathematical expression for the margin, and the end goal is that we're going to take that mathematical expression for the margin and then say we're going to try to make that margin quantity as big as possible, subject to the constraint that for all our training data, these things hold. Right? For every example that we have that's positive, this thing's going to be true. For everything that's negative, this thing's going to be true. Okay. So that's the plan. So let's try to write down the margin. So to start, we can define these x minus and x plus points, which are just any 2 points that sit on the 2 opposite ends of the spectrum, of the margin. Okay, so the first one is, for the -1, let me just find where I am. Is that real?
Outside.
Outside.
Okay. So it's not that, it wasn't a fire alarm?
Oh.
Cool.
There is no smell.
Right. So where am I? Okay, so we were going to say. Oh, okay. So we have 1 point x superscript minus, which is kind of confusing, but x superscript minus plus b is equal to -1, right? So we're saying it's on the margin, so we don't have to worry about the inequality. We just say it's actually equal to -1. Okay, so, all right, so now what can we say about the point that's exactly opposite x minus? What was that?
W transpose x. Left hand line on the margin plus b plus
Equals +1. Yeah, that's one thing we can say. But that doesn't really relate the two. Is there anything we can say about the relationship if they're exactly opposite?
Is minus there.
What was that?
X
X minus.
It's minus WT x minus b.
Oh, I never heard of that.
Like the relationship is the opposite, that's right.
No. I think it's more that I'm not hearing you, but that's not what I'm looking for either. So you're probably right. But so I want to write an equation that has both x minus and x plus in it. So how do we do that? So
I need to use the line that actually is the green line.
yeah. So what's the green line?
It's
That's the magnitude of the green line, which is what we're trying to get. That's what we're trying to find. Parallels W.
Normal.
Almost. yeah, normal, right? So it's a normal vector to W because this goes back to I don't know when, I forget when I learned this stuff. It might have been in linear algebra, but it might have been before that. But like if you have these coefficients to define a hyperplane, then the vector that is perpendicular to the hyperplane is the normal vector. And that's what we're looking for here. This is the normal vector. So we can write this. We can write x plus is equal to x minus plus something times w. So we're going to call it lambda. Something times w. We don't know what that something is right now. And that's actually going to be a key part to, well, that's going to be a key part to us figuring out this quantity. So let's try to figure out what lambda is. So we have all this information. These are our tools. We have these things, we have this, anything else? Yeah, I think this is enough to get us to the answer. So let's plug something in. We can plug in this guy right here, right? So this was the equation that tells us that x plus sits on the margin. So we get W transpose x minus plus lambda times w equals 1. Basically,
No, there's B missing.
B.
B, yes. Yes. Plus B equals 1. Okay. All right, so now let's just clean this up a little bit. So we get W transpose x minus plus lambda W transpose W plus B equals 1. Right, so all I did here was just distribute this W into this what is it called? Something solid. Okay, so now what else can we do here? Does anyone see?
That's what's
Yeah, so this thing plus B, we know it's from here, from this equation. Right, so we can plug that in. So this thing right here is exactly that, and is minus 1. So we get lambda W transpose W minus 1 equals 1, and that gets us finally that, well, not finally, this is like almost the last step. So lambda is then equal to 2 over W transpose W. It's not the magnitude, it's the magnitude squared.
Yeah.
No,
Well, the norm squared. The norm squared. So, yeah, right, so what I just said out loud, just so everyone sees it, is that thing. Okay, so we're almost there. So now we want to
Maximize lambda.
Sorry?
So we want to maximize this.
No, not exactly this. Almost, but this is just this scalar. Like this is just this thing,
Oh, okay.
right? Time which multiplies by W. But now what we really want to maximize is really just cramp that space. So we want to maximize. We want to maximize that. Right? You see what that is? That's this distance from here to there. We really want to maximize that. So we can probably write that. Now this is right. This is lambda W, or it's the norm of lambda W. Okay, let's make some more. Let's clear that away. So I don't think we need this up anymore, and it's been recorded, so you guys can rewind it. Oh, I shouldn't have deleted that. Okay. So I guess I just erased more than I meant to, so I'm just erase everything. So where are we? So we have this. We have that lambda equals 2 over W transpose W. We have that this thing, x plus minus x minus, that thing is equal to the norm of lambda times W. So let's plug that in. So now we get W, we can, actually, that's a bad way to write it. Okay, so let's write out what this means. So the norm of lambda W is the square root of lambda squared times W transpose W. You see what I did there? Okay, so now we can plug in lambda. Square root of 2W transpose W times 2W transpose W times W transpose W, and things cancel. Right, so we're almost finally done. So now we get to
4 over W.
yeah, it's 4 over W transpose W, which is equal to 2 over the norm of W. Okay, so that's finally where we're. We've finally written down the margin. This is the margin. So, like I said, the goal then of SVM is to take the margin, maximize it, subject to the constraints that all the points are classified correctly. And so what are those constraints? So let's say we want to max
2 over.
2 over norm of W, subject to
Good minus 1 also. W.
yeah. And so sort of a shorthand way of writing this is the shorthand way of writing this is y times yi times W transpose xi plus b minus 1 plus 1.
What?
It's going to be equal.
So this should be
Greater than equal. Yeah. Yeah. So this is what an SVM would be if it weren't for reality. Okay. So the reality is that this is not all that nice of a thing to optimize, and so what people do instead is they invert this and square it, and they get something that goes like this. Actually, I'm going to write it because it's in the next slide. So they get this. So this is again, this is really just it's not really. Okay, there is some math that just dictates why this is nicer to optimize, but on paper, this is just a surrogate for this thing, which is actually, but this is actually max margin. This is like max squared inverted margin, or sorry, min squared inverted margin, which is equivalent, right? It's the same thing, but it's really just this way for a few convenience things having to do with what software people have figured out how to optimize.
Easier derivative now.
Not that much easier. I mean, yeah, I think from the calculus perspective, it's the same thing. It's just the only reason it's. I don't know, it's probably people have studied quadratic programming. So this is a quadratic program. Probably people who have studied quadratic programming can probably tell you why this might be inherently nicer to optimize than this. But from my perspective, like they're the same program, it's just the way that this is implemented. So yeah, there's well-studied algorithms. You can download code that does it really fast, or at least what people used to consider really fast. And yeah, and what's interesting is that when you look at the solutions that come out of this, you get that there's the hyperplane is defined by support vectors. That's where the name finally comes from. Is that you get these points there's a few points that are going to live on the margin. That's kind of natural to think about because these constraints. I mean, these constraints they're inequalities, but imagine if none of them were equality, if none of them were equal to 1, then you would be able to sort of fiddle with this objective function more and make it a better margin. And also geometrically, you can sort of see it. Like you can keep growing that margin, but if you keep growing that margin, the only way you're going to stop is if you hit some of these points. And so some of the points are going to be touching the margin, and that's why it's called a support vector machine. I just don't like the name because I don't know why it's a machine. Like, what other algorithms are called machines? I don't know. And it's not really an algorithm either. It's an objective function. That's a machine. Okay. So what if the data is not linearly separable? So now all what I just said before gets really messed up because I said we need to keep everything, make sure all the points are classified correctly. If the data is not linearly separable, things get messed up. So actually, with logistic regression and with naive Bayes, and dangerous neighbors, the things you guys have studied so far, this wasn't really an issue, right? Like, yeah, so logistic regression, it's all probabilistic. So yeah, if some points are, if there's some point that's, I don't know why there's pictures like that because that is linearly separable. So let's say you have this. Then you say with probability 0.75 just gets you the right answer, and something like that would be pretty good. Okay, so for SVM, there's two basic strategies for handling linear, non-separable data. And the first one is to soften the constraint, soften the requirement that all the data has to be correctly classified. And the second one is to essentially not, to use a nonlinear decision boundary, which we'll get to in a second. Okay, I see now. Okay, so now we have an example of points that are not linearly separable. I'm sorry, this is what happens when you get a substitute coming using someone else's slides. Okay, so one intuition is what's on the board here, is to minimize, the norm, which was, again, a surrogate for maximizing the margin, and the number of training mistakes. So that's not actually what the equation says. Let me see if the next slide does. No, it doesn't. Okay, so hold that thought, or don't look at the math. Just think intuitively. This is the idea. This is the basic idea we're actually going to try to emulate with math once we realize these things that become difficult, that make things difficult. So the idea is we're going to say, so we're going to say, let's try to, min W transpose W plus C times, oh, I did that wrong. Okay, plus C times the sum of some loss function over X, Xi, over all the X, all the data. Okay, and the loss function, the most natural loss function is just, did you get the answer right? Did you classify it correctly? And if you write it that way, that's where you get these red bullet points that Drew wrote in these slides, right? It's not a quadratic program anymore. You have this very, very nasty sort of step function that just like as soon as your hyperplane or your W parameters moves into a space where it misclassifies something, that objective function jumps up very suddenly. So it's not smooth, and that causes problems. And then the other thing is it doesn't distinguish, it doesn't distinguish near misses from really bad mistakes. Like if you're, just like I said, when you, actually let's draw a picture. So, let's say there's a plus that has to live here. Actually, I don't know. Let's say there's a plus that has to live right on the edge. That's not that bad. In reality, right, from as humans looking at this, we can say, okay, well, if that's the best you can do, that's not that bad. But if there's one there, that's really bad. And this loss function thinks these are worth the same penalty. So those are two problems with this basic idea, although there is still something attractive about this because this is really what we want in the end often. A lot of times we really care about just the true, how often you get it right and how often you get it wrong. But what we're going to do instead is we're going to replace it with a hinge loss. So it's something, this is a whole thing. So we're going to replace it with this thing where h of x looks like, it looks like this. So this x-axis here is going to be, let's see if I can get this right, what we wrote over there, which was y times w transpose x plus v, I guess minus 1. So this is the 0 point. So this is, sorry, this is really messy. Okay, so this is a hinge loss, and what the hinge loss does is it says that if you, this is the classified, this over here you classified correctly because you got this number to be greater than 0. If you passed here, if you're on the negative side of this, that means you got it wrong. Right? Because remember that the constraint was y times w transpose x plus v is greater than or equal to 1. Right? So if you're on this side of this this shouldn't be part of this. If you're on this side of what's it called? This number line, this dimension, then you got it wrong. But the hinge loss is it's kind of nice because if you go over a little bit, you only pay a little bit. If you go over a lot, you pay a lot. And the definition of it is that this is actually going to be, it's right here. It's the max of 0 or, so let me do this right. I have it written down. times W transpose X plus B minus 1. It's max. Yeah. Yeah. So is that correct? So if it's positive, then it's going to get like I think it's a negativeness. So yeah. All right. Okay. So what we want this number to be positive, and if it's positive, we get 0 penalty. If it's negative, we get this penalty. Right, we get this much penalty. And it's linear with respect to how wrong we are. So I guess in contrast, right, if we draw the true sort of 0-1 loss, it will look like this. Right, because again, if you're here, you're doing everything perfectly. But if you cross that line by even an infinitesimal amount, you pay the full penalty. Like here we're saying, you don't pay that much if you're a little bit wrong. Okay, so that's what the sort of, and then this parameter, this C parameter trades off between how much you care about getting things right versus this thing, how much your margin, how big your margin is. So if in fact, if you set this to infinity, then actually both of these become equivalent to the original SVM we had. Right, because as soon as you get anything wrong, you get, well, assuming you define the infinity times 0 to be 0, just set this to a really, really big number, then this becomes equivalent to the original problem because, right, you want to find the maximum or the minimum norm or the maximum margin W subject such that you don't incur that infinite penalty. Right. Okay. Okay. So then this is not really a QP. This is no longer. This now doesn't look as nice as the other quadratic program that we have up there. So the trick is to write it this way, which is the same thing, but using a slack variable. So now we have this funny, that's a psi, I think, xi, but it's, I don't know, everyone uses psi for that, but it's just, no one knows what it is. So that now is the h of x, and you can sort of, if you stare at it long enough, you'll see it, that's the same thing, right? So it's like this constraint sort of looks like what we said, what we have defined here, right? And the idea is that psi has to be greater than 0. If psi wasn't greater than 0, then this would probably, I think this would lead to that expression without the max. But because you have the psi greater than 0, you get the max. So you never pay penalty if you get this right. Yes. Yeah, and you see, if you just ignore the constraints, if you take on faith that psi is the h of x, and you can see that this is exactly the same equation I wrote there, but then okay, and this is a quadratic program. It's one of these really cool, like the slack variable trick is really, really cool and really elegant when you sit down to work through it. But basically, we've written something that looks like not at all a quadratic program. Like this hinge looks really nasty. It looks like, it doesn't look quadratic for sure. It just suddenly jumps up, but you can represent it instead with constraints. But that's kind of, I guess that's kind of optimization details, which do become important to get to know what optimization algorithms are for different types of problems. But maybe in this context, it's not super critical. But I guess backing up the idea of a quadratic program is an optimization of problem where you have an objective function, the thing that you're maximizing, that's a quadratic in vector space. And you can add linear terms, so this is a linear term on the right, so that's okay. So linear plus quadratic is still quadratic. And subject to linear constraints. So all these constraints are linear. And if they get non-linear, then things get more complex and you have to deal with other types of optimization algorithms, but quadratic program solvers have been well studied and highly optimized for this particular task. Okay, just make sure I don't miss anything in these slides. Yeah, so are there any questions about this kind of stuff so far?
Hx is equal to minus x, or you can choose any function,
Any function.
any linear function, if x is less than 0.
What do you mean? I mean, so I'm using this, yeah, I guess I'm using it as a shorthand, right? So h of x, I'm calling it this,
Yeah,
is this. But in general, you can use, I mean, the hinge functions exist for any other function. You can take this, you can plug in anything else here. Is that what you're saying, that a hinge might not necessarily be for this discriminative function? Or this is not, this is like the correctness function of the classification problem. Yeah, question.
The two axes here, they're like two features, right? So I don't know, but maybe I don't know if you can, based on these two features, maybe make a third feature out of them,
Yes.
and you'll have it in 3D, and maybe you can give it to-
That's the second trick. That's the second strategy. I'll show. Yeah, that's exactly it. There's some slides at the end of the deck about that. So if you are willing to use a more complex model than a line or than a hyperplane, then you can extend your feature space, and there are ways to do that. Did you guys do that for logistic regression? Is that, or are you just coming up with that on your own? Yeah. So that's cool, because that's sort of that actually leads to why SVMs got so popular, because the preview for next class is that I'm going to show you how to do that by creating that extra feature, but in the next class you'll see that you don't actually have to explicitly create that extra feature. You can actually compute sort of, how do I say this without giving it all away? You compute values that compare two data points that are equivalent to if you expanded the full data, the full feature set to this very big complex space, and then computed the distances. It's hard to explain without getting into a bunch of things. Like the next class, we're going to look at Lagrangian duality, which leads to the kernel trick. But I guess the preview is that's what led to SVMs taking over everything in the 2000s, right? And now that's sort of waning with the advent of deep learning, we can sort of look at it in perspective and say, okay, well that was exciting, but what can we learn from it, and why did we get overly hyped about it? There was a little bit too much hype in the 2000s about it. That was when I was in grad school. That was when Drew was in grad school. Every paper at machine learning conferences had max margin in the title, so it was an exciting time, but now we can look back on it. So, I guess, let me show you, so like I said, this C parameter is this trade-off term, and this actually leads to a lot of headaches, and it's very powerful. So now we have the ability to say, well, how much do we care about actually classifying? But instead we just maximize the margin and not care about, I mean, it doesn't really make any sense, but we can maximize the margin and not care about, or rather minimize the norm, minimize the complexity of our hypothesis, but not care about classifying correctly. And in practice, you have to find that trade-off. You have to find, this is related to the bias-variance trade-off. It's almost the same thing, but not exactly. You have the trade-off between this norm term and this loss term. The norm term here and the loss term. Right, so this thing loosely represents, again, I forget if this is bias or variance, but it represents the complexity of the model. Right, so the bigger this is, the easier it is for you to overfit. And then this represents how well you're fitting your training data. Which I guess it doesn't fully map to bias variance, but it's the same intuition. It's that You want to trade off how complex your model is versus how much you fit in. Okay, so let's look at some MATLAB code. Not code, but some plots. So this is a, I guess there should be a link. Hopefully there's a link on the website for this code you can download. Let's see. So we're going to generate some data and try to see what happens when we change C, that trade-off parameter.
Equal.
All right, so X is now, this is 2D data, it lives in the columns, so each column is a data point, and then Y is the labels, just generated in order like this. Okay, so let's do, okay, so this last number here is the C parameter. Actually, can you guys see that? Okay, so let's see what happens. That could have been a disaster. Okay, so this is what we get with C equals 1. So you can see that there's a bunch of points that I think these can be linearly separated. I'm not sure. No, they can't. The green definitely can't. So these can't be separated. So it's just giving up on those. Let's go through the notation. So obviously red is red versus green. You're trying to classify red or green points. It's 2D data, there's 2 features. And the blue line's the decision boundary, and the red and green lines are like the ends of the fat margin. And then it's drawing an X on the points that serve as the support vectors. But then these other circled points, it's kind of hard to see, but there's other points that are circled that also influence the decision. Because they cross the boundary, and so they go into the, or rather they have some non-zero hinge loss. Right? They have, you can think of it as that way. Like in the objective function, it's this one. All the points that aren't circled have 0 here, and then the points that are circled have some penalty. You're paying some penalty for it. So they have influence on the decision. So let's try changing the C. So let's make it really big. So this is the same data. Okay, so maybe this is the best I can do. So I made it really big, and it's not getting any better. So this is one of the things that can happen is that so if the data is really not linearly separable, then big values of C are kind of equivalent.
Can you reduce C?
Yeah, I can reduce it. Yeah, I'll do that next. Yeah. So what actually, in practice, something you might discover when you work with these things is that it messes with the it messes with the scaling of the optimization. So if this term is really, really big, this hinge penalty, the penalty is really, really big. Your quadratic program will spend a lot of time trying to fix this and not spend a lot of time doing this, and that's not really what's going on. That's being super hand-wavy, but sometimes you'll find that the optimization takes a lot longer to get to the same answer. Right? This got to the same answer. In this case, it was a tiny data set, so we didn't notice it, but I'm almost certain it took longer when I set C to 1,000 than when I set C to 10. Okay, so let's try lowering it. So let's do 3.1. There we go. So look how awesome that margin is. It's a really big margin. No, I mean, I joke, but that actually is maybe a better solution depending on how much we trust the noise. Right? It depends on your application. There are many cases where this is like totally random noise, and you just want to see that it's left and right. And you just want that, and that's the simplest solution. And that group will generalize the best. That's the key, is that you want this to, right, when you get a new batch of data, will this one fit better than the other one that was like kind of like this? we don't really know. I forget. I don't know what the data generator is for this. Let's try generating other batches to see what happens. But I didn't expect it to be completely unseparable. So 1.0 will start out. It's weird. I don't know. When I did it at home, I was getting separable data.
Try generating like large data.
Sorry?
Let's try like generating large data sets that like 100, 500.
Yeah, sure. So I just increased it by order of magnitude. I mean, it doesn't help.
So it's now obvious that like in the previous case we put it like in the middle, like horizontal line. So the line that is a bit with the slope is better.
Oh yeah. So
it's now obvious
it looks
like it's better.
Yeah, it looks like this is actually better. So let's try lowering the C and see what happens. We'll get that sort of oversimplified model. I guess that's too much. So I think with more data, you don't make it. That's the thing is with a small amount of data, it was it really trusted the margin. It really cared about the margin term, not the loss term. Now there's enough data to tell it that it shouldn't straighten it out, keep it on a diagonal. It's gonna stick to that.
So what's the difference here between support vectors and margin vectors?
There's probably only 3 support vectors. So if you think about in 2D space, to define the decision boundary, you always need 3 points exactly. So there's only 3 points that are going to be on the decision boundary, which we can't find in this image. I don't know. No, I can't.
No.
But according to the legend, it seems all those points are the
So
support vectors.
these are not support vectors.
So
Oh no, they are. Sorry.
Yeah.
Sorry. These are not margin vectors. Yeah. Okay. So yes. All right. So then the question was about support vectors or margin vectors?
The difference between support vectors
And margin vectors. Margin vectors are classified correctly. They're the support vectors. In this case, it's going to be 3 support vectors. I think this is probably wrong. And sorry, this is it's going to be on the internet. I think it's going to be D+1 support vectors. But is that true? Maybe it doesn't generalize to high dimensional space. At least in 2D space, you need 3 support vectors to define the hyperplane. But in all these points that you can't separate are going to be also support vectors. 3 margin vectors, and lots of support vectors that we can't separate. Let's try increasing C and see how much higher this can get. So if we set C pretty high, it's not. The decision boundary seems about the same, but we get a smaller margin. I don't know, like this one's. Oh no, there's probably a green point behind there. You see what I mean?
Yeah, it's
that's
definitely
probably-
green.
Yeah. Well, okay. So here's the story with this is that the right C value is not something we know. There isn't an algorithm for it. People have been trying to figure this out for a while, but there isn't. It really is just data dependent. It's really the best algorithm that most people know about, that I know about, is just to try it on cross-validation. Right? It's to try a bunch of different values of C and fit that to basically the difference between, it depends on, to fit that to the circumstances regarding the features you have and the amount of label noise you have. Yeah, it really just depends on what features you have too. So it's really hard to figure that out just by looking at the math.
So support vectors are those which are either on the wrong side or between the 2 margins.
Yes, and another way to think about it is that if all the points that aren't support vectors, if they weren't in this problem at all, you'd get the same answer. Yes, so if all these red points here and these green points here that aren't circled, if I deleted them, which
The answer would still be the same.
yeah, you still get the same answer. And that's one of these interesting things about a non-probabilistic model. Right? It doesn't care Right? It doesn't care that, you know, in some models would care that we did really well here. Right? They would say, oh, you did this, you put this really far from the decision boundary, and you got it correct. So you get, you know, extra points for doing that. But an SVM, as a discriminative model, doesn't care at all about that. You know, there could be a point over here, and you get the same answer. So, you know, in some ways that's good. In some ways that's usually what you want, but in some ways that's not. Depends on your application. Okay, so the next sort of trick, this gets to the next trick that you mentioned of, you know, so if you have, here's a very simple case that is kind of trivial, is one of these examples that people like to give, or people would give before SVM. I think historically this story isn't actually true. I think SVM was originally introduced with the fix for this. So I don't know if it actually embarrassed SVM people at all. But if you think about linear classifiers for sure were introduced before people figured out this trick, right? So a linear classifier can't handle this, but this is a really simple thing, right? It's just, I mean, assuming this generalizes, you know, it would be natural to say, oh, let's just predict all blue points are left of here, all blue points are left of there, and anything in between is white. That should be pretty easy. It's not a very complex model, arguably. It's 1D, so it's kind of complex, but it's certainly simple enough that we should have computer algorithms that can handle this. So the way to do that with a linear classifier is to do this, is to create another dimension, and such that you know, that you compute that second dimension from the original value, from the original data. But the original data was just the horizontal axis, but you know, as people who've taken, what's it, 6th grade math, I don't know, we know that we can square numbers, so we can do, I don't know, I forget when people take these things. So we can square them, and so we get this sort of, you know, curved shape, and now this becomes linearly separable, right, with a margin, with a pretty good margin. So this is a trick that we can do, and we can generalize from this. We can say, okay, well, we don't just have to square the data. We can come up with any deterministic function of the data. Like as people who understand the domains of the data that we're collecting, people who are using machine learning, we can always think of, you know, we can say, like this happens a lot. When people are counting words in a document, people often take a log of that because they know that, you know, the raw count sort of grows linearly, and then therefore the more often this word appears, the stronger your prediction is going to be for that particular classifier, and that doesn't make sense. What you really think is that there's diminishing returns. So if there's 100 occurrences of the word versus 1,000, you don't really care. So often people will just look at it and realize that it makes more sense to think of this as a log count than the actual count, or log count plus 1, to avoid the minus or the negative values. Yeah, so this is an engineering issue, right? You say, you know, here we engineered that. We saw the 1D data and we said, okay, well, we need to figure out a way to sort of separate something in the middle, and so quadratic is a good way to do that. But if things got more complex, if there were some white points over here, quadratic wouldn't really help us there. Or it would help us a little, but not all the way. And then the interesting thing about this is that this lets us separate any data in a way. There's lots of caveats here. In fact, I think it's kind of a, if you wade through the terminology here, you can sort of figure out that it's saying something's kind of trivial. Basically, it's saying that if you have a bunch of a bunch of distinct points, so they're all different values, and let's see, and you have some mapping from the original features to some new feature set space, then, and the new feature space, or the new feature values of x's are linearly independent, then the points are linearly separable. But I mean, this part's the part that I think is a little bit silly, because this thing is sort of obvious. So the hard part is getting this to happen, right? Getting these It's not actually that hard either, but normally when you come up with a feature representation, like you square one of the features, like we did in the last slide, you wouldn't get this property. You wouldn't get that the points are all linearly independent. But one way you could do that is if you use indicator vectors to say, is this point, 0.001, sorry, if you use indicator vectors for each of these points, you can just say, this feature, there's some feature for this point that is just 1 for that point and 0 for everybody else, and then everything's linearly separable because you're basically just saying, you're basically just labeling points in n-dimensional space. That's taking that lemma or the theorem a little bit to the extreme, but that's kind of what it's saying. But the point is that we can engineer features as complex to make anything separable. And so that's dangerous, that's bad, because that means we can, right, we just sort of went against everything we just started out doing. We said we want simple explanations. But now we can say, okay, well, we can use really complex explanations, maximize the margin of that, which doesn't really necessarily mean that, it doesn't mean that when we maximize the margin in the high complex, okay, let me try to, this is a very interesting idea. So let's say there's a complexity
Does it become
scale.
something like overfitting or something?
Yeah, so that's what I'm trying to get to. So we can overfit by doing this because let's say this is complexity. And intuitively, again, being loose, there's math that can back this up, but intuitively, we want the lowest complexity model that fits our data. That's the way the best way to do automated science. So what happens is when we say we have a lot, let's say lines are this complexity, but then we say let's maximize the margin for lines. We sort of reduce the complexity a little bit when we do that. So we get something that's maybe here. This is SVM. This is W transpose X plus B. Right. This is just a straight linear classifier without a margin. This is with the margin. But now if we do this thing where we do this feature map, we get a feature map that's like this complex. Let's do phi of X. So we do this mapping that makes things more complex, and then we do SVM on it. So we sort of make it go back a little bit. But we don't know how far, we might not go back far enough, and we might still have a really complex model. So this is one of the dangerous things that can happen when you have this much power to come up with features. But the thing is, it's not really that scary because you have that power in any setting. You can always engineer features. You can always sort of combine them and mix and match them and square them and log them and exp them. You can always do lots of things to your data to make them nicer in some very engineered way. Okay, so yeah, I guess that's what this slide is trying to say. So yeah, so we can always, right, so, yeah, here's a, it's hard to even see this. These are just like random points that are blue and green, totally random. And then you can devise a feature map that can linearly separate in the high dimensional space, but that's meaningless, right? So, and then again, even if you do that and you maximize the margin, it's not going to help you. You're still dealing with a thing that's clearly overfitted.
Is there a relation between the number of points and the dimension of the feature map to general?
Yeah, there is. So the number of points, or the bound on how many features you need to fully separate everything, fully separate all the data, is n, is the number of points.
Should be greater than.
Sorry.
So the dimension should be at least equal to the number of points, right?
Well, if you want to overfit, I mean, yeah. I mean that using more dimensions than the number of points, which sometimes people do, is a recipe for overfitting. But the key is then if you set C right, then maybe you can make it up. If you set C to really care about the margin, right, to not care about the loss that much, you might make it up and get back here, and get a better model that has better loss, better predicted accuracy, but still has not too bad complexity, and so it doesn't overfit. But the danger is this: is if you just you set C so you only reduce the complexity a little bit. And you're overfitting because you engineered some really awesome features. Yeah.
I don't know, but I'm just wondering, what's better to do? Is it better like to keep adding dimensions, or just find one complex mapping function and just add one dimension?
That really depends. So, I mean, this gets to other aspects of machine learning, like feature selection and feature discovery, I guess. Right. So you can always mix and match. Well, okay. Let's put it this way. This is going to be. This is going to get to some more guidelines as to how to navigate this problem, which is it's not only a problem. It's the amount of power you have as a data scientist. You get some data as input, but you can manipulate it in many ways, and then pass it into some classifier. And designing these feature manipulations is kind of an art. It really depends. You have to understand the domain of the data, where it came from, what the numbers represent. And if you don't understand what the numbers represent, then you can start doing kind of arbitrary stuff and just see if it works. Not the best practice, but a lot of people do it, and you can be successful doing that too. Like, for example, just that blanket question of, do we add another feature, or do we use a big feature map? It really depends on the feature map, it depends on the data, it depends on the domain. Okay, so this stuff is a preview. Okay, so all right, the last thing that we want to end on is I mentioned that SVMs have been connected to probabilistic models. It turns out that this hinge loss, right, the red line is the hinge loss, looks a lot like the log loss, which is another way of viewing logistic regression. Now, I'm not sure if this is how did you guys look at the log loss, or you just?
So the expression that is written log of 1 plus.
This one.
Yeah, that was starting logistic regression.
Okay, so you did learn this one, because you can also just sort of view it as optimizing this. But when you take the log and you invert it, I guess. Oh no, you don't invert it. You take the log and you try to minimize it instead of maximize it. You get this thing, which is the log loss. And that's this blue curve, which is kind of the same. Right? It's kind of the same. It's not exactly the same, obviously, but what some people have done in other applications. I've seen some papers that do this, where you can sort of scale the log loss so that as you zoom out on this, it sort of looks more and more like the hinge loss. And so you can people have used it to try to optimize a hinge loss like function with a smooth optimization, like a gradient-based optimization. Because here we have this annoying point that's a hinge that has no derivative, and so it can cause some problems with optimization. And so sometimes we use a log loss or a scaled log loss to simulate hinge loss, but allow you to take derivatives everywhere. But here's the downside, right? So the story seems to be that these are kind of the same thing. So why don't we just use logistic regression so we can get we can get probabilities out of logistic regression, which we can't get out of SVMs. So there's a lot of benefits to logistic regression. The thing that's bad is that these never go to zero. Right? This little sliver here, right, all the way to infinity, at least on paper, is always non-zero, which means that you don't have this phenomenon that we have in SVMs, where right a lot of those points you don't care about. The points that are not support vectors, they have zero influence on your decision. You can do things like compress your data because of that, because those points have nothing to do with your final learned model. But with this version, with logistic regression, those points have some influence. Now, of course, you can always say, okay, well, after this point, let's stop worrying about it because it's really tiny. But on paper, it's definitely less elegant as a result of that. But yeah, so they're strongly related. And then, of course, logistic regression doesn't fit as a quadratic program. So that has some practical implications. We want to be able to plug them into our off-the-shelf optimizers sometimes. Most of the time, depending on who we are. If we're researchers, we might want to sort of do it by hand ourselves. But if we just want the answer, we want the learned model, using the off-the-shelf quadratic program optimizer would be more ideal. Versus this thing, which I don't know. What did you guys learn for how to optimize this? Did you guys use? Gradient descent. Yeah, I mean, there are some off-the-shelf optimizers. I mean, there are off-the-shelf optimizers for these kind of things, but they're not as, they're kind of like logistic regression solvers. Or they're just gradient descent where you then have to deal with, you're doing the optimization, which we can all do as smart people, but you have to code it up, and that's annoying. Okay, so is there anything else? All right, so I think that's it. So next class we're going to talk about the kernel trick. So the kernel trick, like I said, is going to be, that's what made SVMs take off, and it's basically a cheap way of doing that feature expansion. And so feature expansion, what we showed on the slides today, it's expensive because if you want to need a complex feature space, you have to store that complex feature space. But with the kernel trick, this slide, you're going to be able to avoid that. You can basically, it's magical. We'll see. You can figure out, you can do these things with basically like infinite feature spaces, and it doesn't cost you any more than it would have at the limit.